Today is the last day of covering, this week is the last week of covering material, new material. Next week we'll have 2 review days. And I'm not a big fan of this, but we've got Tuesday, Wednesday to review, and then Thursday is the final exam. I would rather have you guys get a couple of days break between reviewing and coming in for the final. It's just the way the cards fell. So next week there is still class. Please come. In fact, if you're someone who doesn't normally come, even more reason to come, because it's opportunity just to review and just ask questions. I don't usually set anything up for those review days. I don't bring material prepared. I think part of the handoff there is that I give you a practice midterm and a practice final, and I open up all of the unit test questions for you. So you have a ton of material to ask about, and I'd rather we answer your questions than what I think your questions might be, because I'm usually wrong. All right. Last week we were talking about reactions at the alpha position, and we saw the alpha-halogenation reaction. So let's say that I wanted to get to this alpha-bromoacetophenone, or I could call it bromomethylphenylketone. What are different ways that I could get there?
Br2 and HCl.
Br2 and HCl. I know I need to add a halogen, and that halogen needs to come in its elemental form. So my OChem 1 students right now, they're learning about all the different reagents. And I had some students that were giving me reagents like this, HBr2. So they're just conflating HBr being a source of bromine and Br2 being a source of bromine. Here, HBr is one of our byproducts. We want to add Br2 and acid. Now it's interesting you said Br2 and HCl. Did I give HCl as an example? Because I would just say any hydrogen source is great, hydrogen ion source. HCl is a good example, but in class we actually use iodine, right? Okay, that's why. That was me giving a specific example. You go to our OChem or our Gen Chem 2 labs, and they'll do iodine with HCl. But any acid is going to do the job here. Is there another way that we could get there? What else? What other reagents could I add?
Br2 and sodium hydroxide.
Good. Now, if I do this, I'm going to want to be incredibly careful about the equivalences that I use. If I have Br2 and sodium hydroxide in excess, this reaction is not going to stop at alpha halogenation. It's going to continue halogenating the alpha position. And in this case, it's going to continue until I get down to a carboxylate salt and bromoform, the bromine relative of chloroform. So I'd have to be really careful about equivalences. In fact, this is maybe not even a reaction I want to run, because let's say there's 100 molecules of acetophenone. That first molecule that gets alpha halogenated is now far more acidic in these basic conditions than any of the other 99 molecules of acetophenone. So even if I control equivalences, I might get a runaway reaction where I get a lot of bromoform side product. So I'd have to be careful. I would actually want my acidic conditions here if I'm going for just one equivalence. The last way that we can alpha halogenate is through radical halogenation. And this is exactly like what you saw in OChem 1 when you saw radical halogenation of alkanes and allylic positions. Let's say that we have this ketone, which means that it has two different side positions, one more substituted, one less substituted, and I add Br2 with light, or if I wanted to, substitute this for N-bromosuccinimide. And because the radical here is going to be conjugated to the carbonyl, we're going to get a resonance stabilized radical. Which position do you think the Br will add to? The more substituted or the less substituted?
More.
Tell me why you think that. In acidic conditions, the Br selectively goes to the halogen selectively goes to the more substituted position. In basic conditions, it goes to the more substituted position. And we explained that by the stability of the enol that forms, or the enolate. So what do you think here says more substituted?
Stable radical. What is that? No, the dot.
Yeah, that's a radical.
It's a radical.
More substituted radical is more stable, just like a more substituted carbocation. Not to mention, the resonance stabilization gives a more substituted alkene as well. So 2 reasons. Primarily, though, it's the stability of the carbon radical. There you go. Alpha halogenation in radical conditions. And because I like to show what happens here, I'm going to give it to you like this. Here's the radical that forms. You guys should remember that Br2 in the presence of ultraviolet light splits into 2 bromine radicals. That first bromine radical is here to extract the hydrogen. It's the second bromine radical that will actually add on here. And the resonance form that we have of this radical places that unpaired electron onto the oxygen as well. So you can see that once again, we do have the more substituted enol intermediate.
Would that be considered that's not a enolate, right? Because it's a radical, not a charge.
So I would say it's an enol radical. I haven't actually heard a term given to it. But in the same way that you can have an allylic cation, an allylic anion, an allylic radical, you could describe this as a carbonyl radical because it's conjugated, but I think because it has resonance with that enol radical form, that'd be the best thing to call it. It's not an enol, it's not an enolate, it's an enol radical.
So I noticed you didn't do any arrows in the resonance.
Sure. I'm not doing a mechanism right here. I'm just showing the 2 forms of the intermediate that exist.
But if we were to do the resonance, how would we do?
Sure.
Like the,
What does the electron arrow pushing look like? To get from this form to this form, notice that a carbon-carbon double bond has to form. The carbon-oxygen double bond has to break. When bonds break, the electrons break towards the more electronegative atom. Okay, well, this isn't heterolytic breaking. This is actually homolytic. So when the CO bond breaks, each atom gets one of those electrons. That's how the oxygen is going to become the oxygen radical. But the carbon doesn't want to hold on to its radical electrons. So the carbon takes its radical electrons into the bonding region, where the carbon radical also joins with its electrons. Notice that what I have are fishhook arrows. So I don't have this. I I have this, which is indicating the movement of just one electron. Carbon radical forms a bond with another carbon radical electron. Meanwhile, an oxygen radical forms. I think what a lot of people would like to do in a situation like this is they would like to say that the carbon radical goes to the oxygen and then the pi bond moves between the carbons. But this is like taking electrons and playing a game of fetch, and they don't do that. Make sense? Cool. All right. There is another reaction that I want us to learn, which is alpha-alkylation. You're never going to believe what happens here. We're going to add electrophiles similar to the ones that we did in OChem 1 that will allow us to create carbon-carbon chains from the alpha position. It's going to require that we have basic conditions. We need to make that alpha carbon into a nucleophile, a good nucleophile. So I just want to give this generically. If we have this carbonyl, and let's say that it has just 2 hydrogen positions, 2 alpha hydrogen positions. Instead of a methyl, we'll make it into a CH2 group. If I first react this with a base, let's say a sodium alkoxide, so like sodium methoxide, sodium ethoxide, sodium tert butoxide. Or if it's an aldehyde or a ketone, sodium hydroxide would work as well. And then, after turning it into an enolate, then I introduce some sort of alkyl halide. I form a carbon-carbon bond between the alpha carbon and that alkyl halide carbon. So at the alpha position, I've added this new alkyl group. And if you've got 2 different alpha hydrogens, then you can repeat this process.
This wouldn't work with an aldehyde, right? Because the alkoxide would attack the carbonyl.
So in any of the carbonyl conditions, the alkoxide could attack the carbonyl.
Oh, okay, so good.
The thing is, those reactions are easily reversible. If the base does acyl addition to the carbonyl, then the carbonyl can just go through elimination and kick that base back off.
Oh, okay.
If we have an ester, we really have to make sure that any acyl addition that happens doesn't change the ester linkage.
Right.
So if you have a methyl ester, you want to use methoxide. Ethyl ester, ethoxide. With aldehydes and ketones, you could even use sodium hydroxide because it's still reversible. Okay, so that's our generic idea. Let's look at a couple of examples. I'm not going to lie, the most common reagents to see here are the malonic ester and the acetoacidic ester. Acetoacetic. Still hard to say. Do you remember these esters? Why did we talk about them? Where did they come up in our notes?
With like acidity of hydrogens.
Yeah.
Comparing them.
And what did the malonic ester and the acetoacetic ester have in common compared to all of the other alpha hydrogen acidity levels? They were lower in acidity.
Well, and the acetoacetic was lower, right? Because of the resonance.
The pKa's were lower because they have increased resonance. So if I'm going to run these alpha-alkylation reactions in basic conditions, then it works best when I have my most acidic alpha hydrogens. So this is just incredibly common to alpha-alkylate these two esters because they have the most acidity at their alpha position.
Which one was the malonic? Maybe I didn't mean the other one.
Let's look at it. Actually, first I'll give an example with acetoacetic. Yeah, I'm getting better. You gotta say the exact same sound twice. I don't like it. Okay, so let's say that we have methyl acetoacetic ester, otherwise called methyl acetoacetate. Now, in order to make this into a nucleophile, I need to react it with a good base. I'm going to react it with sodium methoxide. I cannot use hydroxide for this because it will hydrolyze the ester. I don't want to use ethoxide for this or it will transesterify the ester. Sam, give me a number between 1 and 8.
6.
Okay. 6 carbons. I'm going to do a 5-membered ring with a chloromethyl group coming off of it. Chloromethyl cyclopentane. I'm aiming here for primary carbons because an alpha carbon is still a relatively good base, and I don't want to risk doing any elimination instead of substitution. And look at the product that it gives me. It can be really challenging to make sure that you add the correct number of carbons here. So what am I going to encourage you to do? Count your carbons. And better than counting, map them. That way you know what everything should be connected to. So one way to count your carbons is just to say acetoacetic has 1, 2, 3, 4. 1, 2, 3, 4. And my chloromethyl cyclopentane has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I have the correct number of carbons, but it doesn't really tell me if everything's mapped correctly. So I'm going to start numbering from the ester. I'm going to number to the alpha carbon. The alpha carbon is the nucleophile, which is going to attack the electrophilic alpha carbon. Alkyl halide. 1, 2, 3, 4. And then it's done? Well, if I want to, I could have added 2 equivalences of everything. I could have double alkylated. Or, because I still have a highly acidic alpha hydrogen, I could just run another elimination another deprotonation and a second substitution reaction. Let's do another example with the malonic ester. So you see the similarity and the difference between them? Both of them are beta carbonyl esters, but the malonic ester is a beta ester ester, and acetoacetic is beta keto ester. Caitlin, what should my base be?
NaOET.
Good. I'm just taking whatever that linkage is, and I'm making it my base. And Matt, give me a number between 2 and 8. 5. So I'm going to do 1 bromopentane. All right, now it should be easy at this point to just say the product will be the malonic ester, but with a 5-carbon chain coming down it. So now I want to do a second alkylation, which means I need to deprotonate that alpha position again. And I'm going to follow this up with benzyl chloride. Can you predict the dialkylated malonic ester that forms?
It's gonna be the same with extra, the
Mm-hmm. It's going to have a quaternary alpha carbon. Yeah, a little clunky, and they can be hard. You know what can make it easier though is abbreviating the ring as pH.
More excited to draw it up.
Good stuff. It can be more exciting, it can look more realistic, but then it can also be challenging to get the angles down. You're really close, except your esters turn into ethers.
Oh.
Okay, so after the first alkylation step, I add this 5-carbon chain. So I'm going to map just to make sure I'm adding everything that I want to. Here, carbon 2 attacks carbon 3. Well, here's carbon 2. So then carbon 3, 4, 5, 6, 7. But then carbon 2 also attacks here at benzyl chloride. So carbon 2, I'm going to call this 3 prime, and then the benzene ring will be 4 prime.
For the reaction, can't you just do 1 NaOET, 2 the chain, and then 3 the phenol? It's like suppose that, or does it have to be
Okay, good question. It's not catalytic. So sodium ethoxide takes away a hydrogen. That makes a sodium enolate and ethanol. And then that sodium enolate substitutes an alkyl halide. That makes sodium halide, alpha-alkylated compound and ethanol. So the base needs to be re-added if I want to do another substitution reaction.
Okay.
It's a good question. It's not a catalyst. And furthermore, I don't want to have these two mixed at the same time. Otherwise, I risk this substituting twice instead of just being substituted once, or this being substituted twice instead of once. So I want to add them step by step. Okay, now my second one, I decided to map them a little bit differently. I'm giving them prime numbers to keep them separate. So here's 3 prime, 4 prime. Does it matter that my pentane chain is on the left and my benzyl chain is on the right? No. It's technically not a chiral carbon. It's got 2 identical ester groups on it. But if we had done something like this and we created a chiral carbon, you've got good chances of getting 50-50 both configurations. All right, now we've looked at the deprotonation of these before. What I want to look at quickly is what is happening in this mechanism so that you're all familiar with it again. The first step is to deprotonate in that basic condition. Make an enolate. And that enolate is in resonance. If you're asked to, on a unit test or on an exam, if you're asked to show all resonance forms, then you show the other 2 resonance forms for this as well. But for now, let's look at the substitution that occurs. It is this resonance form that attacks, but remember, you can show a next step occurring from any resonance form. The carbon takes the lone pair, attacks the partial positive of the alkyl halide. What is that? That's SN2. So how come they don't teach you that in OChem 1? Just because it's a scary looking nucleophile? That's all. And then that's where we're left with bromide as a byproduct. Okay. And then you just do it again. So if you guys are all right, I'm going to leave it at that. Questions? Okay. There's a reaction that doesn't really fit into the rest of the reactions we're going to cover this week, but is so commonly seen in the syntheses that involve these. So it's not really a similar reaction, but it's definitely worth seeing, and this is the best spot to see it. That is decarboxylation. What do you think is a byproduct in the decarboxylation reaction?
One of them, right?
Carbon's got to be in there somewhere. This is organic chemistry. Did you say CR2? CO2. CO2 is the answer. Carbon dioxide.
Carbon. Oh, I know it.
Carbon is in there, surprisingly. What we need in order for decarboxylation to occur. It requires a beta carbonyl acid. What can that carbonyl be? Well, that carbonyl could be an aldehyde, that carbonyl could be a ketone, that carbonyl could be another carboxylic acid. So let's keep it simple, and for now we're just going to abbreviate it as R. But we'll remind ourselves R can be H, OH. It's not very common for it to be an ester, so I'm just going to leave that out. Not that an ester wouldn't work, but that an ester is just not common. Or it could be a carbon chain, so it could be R. You know, sometimes R is R. The conditions that we provide here, is just heat. So we write that as delta. Stick it in the oven or reflux it. And you're going to decarboxylate. And here's the product that we get. It's not a combustion reaction because there's no oxygen involved. O2 is not involved.
Okay.
I want to make some modifications. Notice that CO2 left, obviously from the acid on the right. But what happened to its hydrogen? Where is its hydrogen? It didn't leave. This is balanced. This is stoichiometric on the board.
And reconnected to the beta carbon,
Not beta.
the alpha carbon.
Yeah, CH2 alpha carbon, CH3 alpha carbon. All right, so here's the modifications that I would make. What if we've just done some sort of alpha-alkylation? And so we have these R groups here. Those R groups stay at that alpha position. So here's how this ties in. Acetoacetic esters, malonic esters, those are beta carbonyl carbons, beta carbonyl carbonyls. They both have a carbonyl at their beta position, but they're not beta carbonyl acids. So how could I take something like this last product we have? And how could I get this down to something like this? Yes, sir.
Would it be water and then heat?
Not water. No, but on the right track.
OH.
OH is not a thing. OH radical, OH minus hydroxide.
OH minus.
OH minus. OH minus will hydrolyze the ester to a carboxylate, saponification.
Is it, either OH or like the same R group as on the ends of the.
No, so I don't want an alkoxide. Actually,
wait, this is H3O.
H3O plus,
Yeah.
acid catalyzed hydrolysis. I could do saponification, but I would need an aqueous workup after that, an acid workup. So I might as well just do acid the whole time. H3O plus.
And you can do just H plus.
Yeah, but you need water there too. So H plus and water. So it is best to say H3O plus.
That's what I was wondering.
And then follow that with heat. In fact, you don't have to say 1 and 2 here. It wouldn't be wrong to have 1 and 2 there, but you can just do acid and heat. Notice that there's some things being skipped over. That hydrolysis is taking malonic ester and making it into malonic acid. And then it's that malonic acid which behaves as a beta-carbonyl acid because it is, and it decarboxylates. So earlier when I mapped my carbons, I called this 1, 2, 3, 4, 5, 6, 7, 3 prime, 4 prime. So this is really convenient. I actually just took malonic ester as a means of doing easier alkylation. And then I cleaved off a carbon group. And now I have kind of this molecular scaffold where I can continue reacting with it if I want to. And I love this mechanism. I'll almost definitely not test on it, but I almost definitely always have a bonus question that involves it. I don't always, but I like to because I just like this mechanism. So what I've done is I've actually arranged the beta-carbonyl acid in a specific orientation. This is why heat is required for decarboxylation. It's this orientation that allows the decarboxylation to occur. Notice that there's kind of this 6-membered ring situation going on, where the OH of the acid and the O of the carbonyl, they kind of create the top of this 6-membered ring. It's just not physically connected.
Technically, do you actually have to use the acid here since you already have a carboxylic acid to use heat and it would carboxylate?
Well, that's what's happening. This is the mechanism for this, just heat. So acid is not really necessary here. Actually, you'll see that acid is maybe involved better in the next step. Think about what bonds need to break and what bonds need to form. Tell me some of the bonds that need to break. Tell me some of the bonds that need to form.
They need to form a CH bond and then that CC bond needs to break.
Carbon-carbon bond needs to break. And at some point, a carbon-hydrogen bond needs to form. What else?
That oxygen-carbon bond needs to become a double bond.
CO double bond needs to form, which means that one other bond needs to break, involving the O. The OH bond needs to break. Okay, so let's start at the OH bond. Is it easy to predict which way the electrons will flow when the OH bond breaks? Does H take the OH bond? Does O take the OH bond?
The bond doesn't the electrons.
Mm-hmm. The bond doesn't in the electrons.
The O.
Yeah, because when a bond breaks, it's the more electronegative atom that takes the electrons. Okay, so the OH bond needs to break, and a CO double bond needs to form. So the OH bond is taken by the oxygen to form that CO double bond. Okay, something is going to need to bond to that hydrogen. But it can't be the carbon, it can't be the alpha carbon, because that bond is too far away. The orbitals aren't overlapping. But what can take that oxygen is the carbonyl oxygen. Excuse me. What can take that hydrogen is the carbonyl oxygen. So the carbonyl uses its pi electrons and bonds to the acid hydrogen. And this leaves us with the last thing. The carbon-carbon bond needs to break. Which way would the carbon-carbon bond flow? Because here, there's no more electronegative atom or less electronegative atom.
Which one?
The carbon-carbon bond between alpha and acid needs to break. Should that electron flow towards the carbonyl carbon or towards the alpha carbon? There are two things on the board that I think should tell you which way it flows. Towards the alpha. Give me your reason.
Well, the main one was that C can't take any more bonds.
100%. This carbon already at an octet and gaining a new bond. It needs to lose a bond. Second reason. This carbon is losing a bond. The carbonyl oxygen is taking electrons away from the carbonyl carbon. Becoming electron excessive, becoming electron deficient, alpha carbon can help with that. And I think you can see why that's one of my favorite mechanisms. Isn't that nice? It's very similar to the resonance arrows you show in taking one form of benzene to the other form, except it's really cool process that's happening. Okay, so I think you guys will recognize that this is not that final product. So did I just lie to you and it doesn't actually give this carbonyl? I lied. No, come on.
Something happens.
What happens?
The alpha carbon jumps at the hydrogen.
The alpha carbon jumps at the hydrogen. Not resonance, no, but similar. This won't form an enolate, no, because we're almost always in acidic conditions here. Sorry, not almost always. If you have a carboxylic acid, you are in acidic conditions.
When the oxygen just pull on the electrons, maybe,
Oxygen does kind of pull on the electrons.
and it kicks out the hydrogen.
Yeah. No, actually.
Okay, the hydrogen from the other side comes and bonds and breaks the bond. and-
What is the relationship between these two? I gave you guys a name for it last week.
Tautomerization, that's the word.
Tautomerization. Enol to carbonyl. So this is the final product. Why? Because enols don't form readily. So I'm going to give this an equilibrium arrow, not a resonance arrow. And I'm going to say the equilibrium lies heavily towards the carbonyl. Is this base catalyzed tautomerization, or do you think it's acid catalyzed tautomerization? Yeah, right? If you have a carboxylic acid at the start, you're not in basic conditions. You can't have base catalyzed tautomerization. So this must be acid catalyzed tautomerization to get us to the final product. Now, I would love to just go through the acid catalyzed tautomerization again. But you know, I don't have enough time, so we're gonna keep going. You've seen it. You can do this. And I know you can because I'm pretty sure I gave you this exact molecule. R at the same place, CH2 on the right-hand side. This is the mechanism you've seen. And it does work as the oxygen forms a carbonyl. The alpha carbon deprotonates an acid. And then, in the next step, the carbonyl gets deprotonated. So it is 2 steps for that acid-catalyzed tautomerization. Okay, so you guys can see how decarboxylation would be useful here, yeah? I want to give us a little time to practice and take a short break before we get into some new reactions. So what I want you guys to do is I want you to find a way to make this structure.
And one step?
Oh, sorry, that's not what I wanted. I wanted it to be this. Not in one step, nope. You'll need to decide what your best starting material is. Start from malonic ester or the acetoacetic ester. Find a way to make this ketone. Really close. Very close. There's 2 things that I see wrong with your reaction or your synthesis. I'm just going to leave you with that. Two things that are not quite right. If you want more advice,
Okay, let me.
maybe before you make changes, highlight what you think is wrong, and then I can come back and just tell you if you're
I
right.
think this is right. This stuff. Yeah. Because I'm just looking at this.
Mm-hmm. Yeah, I agree. I don't know that you need H3O plus, to be honest. I think you could do it with just H, or just delta. Just like this shows. Oh, that's not quite what I put there, is it? I
No.
no, because all I have is the delta. So it's not wrong. It wouldn't hurt. In fact, if anything, it's going to improve it. But
I think I see.
okay.
No, the,
Oh, okay. I'm not here to judge, you know.
So then why did you do it here?
Yeah. What is the difference between this and this?
The melodic pieces.
Because I even said R here.
Oh, so it could be.
What's the difference in the functional groups?
is it what?
So you haven't really started from the malonic ester or the acetoacetic ester.
Oh, we're supposed to start.
You've
Okay.
just picked up here. This step is correct. This step is not. You can't add heat
Oh wait, the heat one.
Oh.
to make an acid into a ketone. No. Oh, I mean, like, yes, that works, but I want you to start your synthesis from malonic ester or acetoacetic ester.
What this thing is, this is our,
No. This is not acetoacetic ester. This is a very substituted acetoacetic acid. So I want you to do any alkylations that you think might be necessary. You are right that this would give that final product.
okay, so I will have to add something to get here.
Yep. Or you could show it all over the one reaction arrow.
Did this fix the other thing? The sodium?
No, it didn't. Just as impossible as sodium methoxide. Actually, sodium methoxide was probably a better spot, but I think you would agree it doesn't match your ester.
Okay, hold on.
Is that an ester?
No,
Why isn't it?
doesn't have. Okay, hold on. Let
Mhm.
me,
Okay.
I'll fix it.
All right.
Would this change that to be that? Or is that not?
Step one.
Uh-huh.
Yeah, but it would do it way too soon. It would do it immediately.
Mm-hmm.
So you would never get to add these on.
Okay, so then,
Good. Or don't forget your O.
yeah.
And then I see you added pH, CH2Cl.
It's not, I kind of add a
No. Great first step. We're not going to need that here. It wouldn't necessarily be wrong, but it's going to look more similar to the second example that we gave in terms of you're just going to repeat step one, but with a different reagent at step two. There you go. Need something else on that arrow, Ralph, not just the delta in this case.
Oh my.
This isn't a starting material I've asked you to start with.
Mm-hmm. Oh,
What's different about it?
I'll just go.
Good, good. Yes. Great job. So how do you decide whether to start with acetoacetic acid, ester, or malonic ester? Okay, so you've made an ester and an acid, which is actually not the starting material that I've given you. That's a diester.
But it still matters.
Oh, Oh yeah. I mean, first what matters is acid-base chemistry. If this is an acid, then the base I add just deprotonates the carboxylic acid. Why would it go for the alkyl, the alpha carbon that has a pKa at 11, if it can go for the acid that has a pKa at 5? Mm-hmm. So then the numbering here is just off. Alpha attacks primary carbon. There you go. Did I sign you off yet?
No. Did I not do that? I'm questioning myself now.
Yeah, it would, but you could just do something like this.
It would just be the NaOH.
Because if you do NaOH,
Uh-huh.
you don't get this.
Mhm.
You would get carboxylate.
Okay.
But I can't do decarboxylation with the carboxylate. I need it to be protonated,
Uh-huh.
so I need a
The
carboxylic
H3O.
acid. Yeah. Mm-hmm.
I think that.
So the other question is, you got this R group. Then the other question is, what can I add to get this R group?
Yeah.
And it's going to be the same process.
What?
You took this and you cleaved it. You just had 3 bonds to a chlorine. Then you're going to do the same thing here. Cleave that and have 3 prime onto a chlorine. Just like that. Okay, so one of the questions that you should ask is, how do I know whether I should start with malonic ester and get all the way down to a decarboxylation product, or if I should start with acetoacetic ester and get all the way down to a decarboxylation product? The answer lies in the functional group at the end. What do you have here? Ketone. So if you've gotten here by decarboxylation, that means that at your more substituted alpha position, you also had a carboxylic acid that left. And that is your starting point. Ketone and carboxylic acid. But if you're working with malonic ester, you would have, like we showed here, you'd have a diacid. So this is the group that's getting decarboxylated, and I'm left with a ketone. That tells me that I want to start with a compound that has a ketone. So I'll start with not malonic ester, because there's no ketone there to be had. But I'll start with acetoacetic ester. I've decided to go with ethyl acetoacetate. Last time I gave you methyl acetoacetate. They work just as well. And then I want to do my alkylations. So if I'm going to map my carbons, I'll look at the carbonyl carbon, I'll look at the alpha carbon, and then I have 2 different ways of mapping. I can call this 3, 4, and I can call this 3 prime, 4 prime. This is where I, as the grader, have to give more leniency to you as the person predicting a synthesis. I decided to go with an ethyl ester, which means that my base has to be ethoxide. But if you went with a methyl ester, you have to go with methoxide. It's not wrong if I do an ethyl and you do a methyl. It's wrong if you do a methyl but use ethoxide. Then I'll add in my first group. I'll add in this carbons 3 and 4. And attached to carbon 3, I need to have a leaving group. So I can make that Br, I can make that Cl. I could make it a tosylate. And then I'll do the same thing again. Add in my base, add in my second set of reagents. 3 prime, 4 prime, where 3 prime is attached to a good leaving group. So that gives me my dialkylated intermediate. And then all I have to do is hydrolyze my ester. H3O plus does a great job at that. And decarboxylate it. And I do want you guys to understand, you can show the hydrolysis product before you show the decarboxylation product. But if you were just adding this as a step, step 5 would be H3O plus and heat. It gets you there all at once. But you can show it stepwise. There's nothing wrong with it.
Is there a reason that one an alcohol was left, but this one it wasn't?
Caitlin,
That's a 3O, H3O plus.
alcohol. Where do you see an alcohol?
Sorry, carboxylic acid.
Yes, there is a reason. If we start with malonic ester, and we hydrolyze it, we get malonic acid. It's the same carbon chain, but now it's a carboxylic acid. And if we decarboxylate malonic acid, I'm left with just a carboxylic acid. But if I work with acetoacetate, and I hydrolyze this, I get acetoacetic ester, or acid, acetic acid. And if I decarboxylate that, I get a ketone. So the point is, one of your carbonyl groups will leave. In the case of malonic ester, it doesn't matter which carbonyl leaves because the other will leave behind an acid. It doesn't matter. But in acetoacetic esters, it does matter which carbonyl leaves. This carbonyl stays because it's not the acid that can be decarboxylated. I can't decarboxylate, meaning decarboxylic acidylate a ketone. I'd have to deketonylate. It's not a thing. Don't do it. Does that make sense? So one of our common starting materials will give us a ketone byproduct. The other starting material gives us an acid product. And that's what I was asking you guys before. How do you know what your starting material should be? Depends on the functional group. Ketone, this. Acid, this. Ketone, acetoacetic ester, acid product, malonic ester. Okay, no alcohols.
I'm sorry. I didn't look at the whole molecule when I was comparing. I just looked at the OH.
All right, do you guys need a break? Do you need a chance to get up and move around? Let's try to make it quick, like 3 minutes or so that we can dive into our next set of reactions.
So is this the chapter working on last week's stuff, or is this leaked into the other chapter?
If you look at our textbook, it covers all of this kind of at the same time.
Okay.
But the way that our class is broken down into sections, this belongs in section 22 because it's everything that's happening kind of at the alpha carbon. And we're just going to start looking at section 23, which is confusing because we're still going to use enolates. And we're actually still going to do like addition reactions, which means we're going to use it as a nucleophile still. So they bleed in because it's all very similar. But technically this would be the end of 22.
Okay.
Yeah.
And so I know we've gone over like a bunch of mechanisms, and I know there's a lot of similarities between all the different mechanisms, But are there ones that we should focus more on, or we just should know them all?
Yes, there are ones you should focus more on. The acetal synthesis and hydrolysis, and the acid catalyzed esterification and acid catalyzed hydrolysis of esters.
So you said esterification and acid catalyzed hydrolysis?
Yeah, of esters.
How do you say esterification?
Esterification,
Esterification.
because it makes an ester. So those are the forward and backwards of each other.
Okay.
Yeah?
Mhm.
Acetal formation, acetal hydrolysis.
Mhm.
Acid catalyzed esterification, acid catalyzed hydrolysis of an ester.
Okay.
That's from Unit 4. Those were the mechanisms you guys had to show on the unit test.
Okay.
Unit 5, we actually are about to look at the reactions that give us the mechanisms.
Okay.
And you know what I don't have yet is a written homework for this unit, for Unit 5, which would be a mechanism and a synthesis. And I think it will be meaningful to have it so you can attempt those before you have to do them on the unit test. So I'm going to try and make that this afternoon and send it out to you guys to do. So what I noticed while you guys were doing those problems, what I noticed was just a lot of mistaking the functional groups during different parts of the steps. So a lot of you started with an acid precursor, but you can't do an acid precursor in an alkylation reaction because you need to deprotonate something, the alpha carbon, and if there's a much better acid, the alpha carbon won't be deprotonated. That was pretty much it. Just make sure that you start with the correct starting material. All right. Into our last set of reactions. We're still kind of revolving around the alpha carbon. But here we're going to look at aldol addition. Now, I like Aldol a little bit because it's not a guy's name. It's short for aldol or aldehyde alcohol. And that is the best way of recognizing the product of this reaction. I'm going to have R plus R prime here. Actually, I'm not. I'm going to leave it as R. Two equivalences of this same reagent. And if I interact in the presence of like a weak, a moderate base like sodium hydroxide, okay, so if it helps you, you might want to take one of those starting materials and actually flip it around, because you'll notice that in the product, I've got the R groups coming from two different sides. In other words, it might help you to see it kind of like this instead. And so if R is a hydrogen, then in fact you do get an aldehyde alcohol in the aldol addition product. But what functional group is this? When I introduced this unit last week, I gave you guys a list of new functional groups we'd see. How can we describe this functional group?
Beta-hydroxycarbonyl.
That's it. So the aldol addition reaction gives you a beta-hydroxycarbonyl. That's the goal. Aldol addition, beta-hydroxycarbonyl. So let's do an example and look at its electron arrow pushing then. So out here, I'm going to put two equivalences of this aldehyde. I can really react this aldehyde with whatever I want. Sodium hydroxide is easy to come across, and it's cheap. Now, when I predict my products for these, what I like to start with is my template, the beta-hydroxycarbonyl. And almost always there will be a group here, but that's the simplest beta-hydroxycarbonyl that you could have. Now I just need to functionalize it with the R groups. All right, so take a look up here. I labeled a carbonyl carbon alpha and beta. Here's that carbonyl carbon alpha. Excuse me. Where's beta?
No, compound.
The other carbonyl carbon. And I just realized I made a mistake in my generic example. Excuse me. Can you tell me what my mistake is? I'll give you a hint, it's in the product. What were you going to say, Rob?
It's missing methyl.
It's missing a methyl group. Where? Attached to what?
Aldol one. Carbon.
Nope.
Alpha.
Beta?
The beta carbon is missing its methyl group. So I can see why you might be confused about which carbon is missing its methyl group. But if this is an alpha carbon to the product, that means this is acting as a nucleophile. And if beta is coming from the starting material as a carbonyl, that means it's going through acyl addition, and it is being the electrophile. So beta is being attacked by alpha. That's why CH3 goes to CH2. It's a nucleophile. But beta still has a methyl group that I forgot to show. So there's the methyl group for that beta position. Tertiary alcohol. So let's come back to this. Here is my carbonyl carbon, my alpha carbon of the carbonyl that attacks. I'm actually going to put that above it. And then here is beta, which means the second equivalence, the one that gets attacked. Okay, so a bit of a challenging thing, because when I look at the precursor, it is both the carbonyl carbon, the alpha carbon, and the beta carbon again. So maybe it helps here to draw the second equivalence out. And then label the beta carbon on that second equivalence.
But in the first reaction you showed, you're reacting with both methyl groups, or kind of like uniting, right?
No, the two methyl groups are not uniting. Alpha attacks beta. Beta still has a methyl group.
Well, visually, they're like, no?
Maybe it's not a good idea to.
And there's the R groups. And then there's a phenol with 2 carbons.
We haven't finished drawing the product. Yeah.
Well, how do you know, what I'm saying is, how do you know that the phenol is not the R group? And
In this case, okay, yeah. Well, for one, this is an aldehyde. This looks like a ketone. But if R is H, that makes this an aldehyde.
okay, so it's gonna,
It's going to vary based on your compound. Let's finish walking through how to predict the structure. So alpha attacks beta. Alpha is still attached to these 2 carbons, 1 and 2. So I'm going to draw down from alpha. I'm going to draw this 1 and 2. And from beta, which is the one that gets attacked, I still have this 1, 2, 3. I'm going to call it 1 prime, 2 prime, 3 prime. So beta goes from a carbonyl to an alcohol. Beta is attached to 1, 2, 3. Or 1 prime, 2 prime, 3 prime. So here's the final product that I get. I'm going to just redraw it so we can see it more clearly. That's a beta hydroxy carbonyl, a beta hydroxy aldehyde in this case, an aldol. It's the addition reaction. What type of addition? Aldol addition, acyl addition. A carbonyl is being turned into an alcohol by being attacked by an alpha carbon. Let's look at the mechanism. Because this is another mechanism that you may be tested on in your unit test and on the final exam.
How many mechanisms do I have?
The last final exam in the spring, it had 2 mechanisms that had to be solved on the final. Acetals and esters. Okay, so you'll notice that I've explicitly shown the alpha hydrogens on one of my structures. That's because one structure will turn into an enolate and the other will become the other will be the electrophile. Hydroxide acts as a base, deprotonates the alpha position. I'm actually going to show you the 2 resonance forms. First, my alpha carbon holds on to the electrons, and the alpha carbon shares the electrons with the carbonyl oxygen through resonance. My 2 enolate forms. When the enolate acts as a nucleophile, it attacks from the alpha position. Which means that from my second resonance form, I'll have to show the carbonyl reforming and the alpha carbon taking the pi electrons as nucleophile. Carbonyl reforms, alpha carbon attacks carbonyl carbon. That's acyl addition. Isn't that acyl addition? Carbonyl group gets attacked by a nucleophile. We've seen that with Grignards. We've seen that with water. We've seen that with alcohols to make acetals. We even saw that in acyl derivation. All right, let's not forget I've got water here. I'm going to show that water highlighting an OH bond because water is a conjugate acid. And it's at this point that water gets deprotonated. That's what gives me my final aldol addition product. And it regenerates my base. So my base is serving what function here? Is my base a starting material, a product, or a catalyst? The base is a catalyst. It's being reformed. Good job. Yeah? If we were to name these steps, we would call it deprotonization, or you could call it enolization. One A is just the resonance forms. Step 2 is where we have acyl addition. And then every time you've got a deprotonation, you should have a subsequent protonation, or vice versa. Pretty simple mechanism. It does get confusing because of how long the carbon chains are. All right. The same thing happens with ketones, but we can actually control the regiochemistry. So what I'm going to give us is a ketone that has 2 different degrees of substitution. Here's 2-pentanone. When we take this 2-pentanone through a reaction with sodium hydroxide, and again, that means there's really 2 equivalences of this molecule that will react together. Sodium hydroxide forms an enolate at the more substituted carbon. So the more substituted alpha carbon attacks the second equivalence. This gives us a aldol product, a beta hydroxycarbonyl, that is connected towards the more substituted side of the nucleophile. Sorry, is this our kinetic base or our thermodynamic base? So remember, kinetic is the easiest to form. Thermodynamic is the most dynamic to form. Does this give the most stable enolate or the less stable enolate? More substituted, more stable. So this is our thermodynamic base. Let's take the same ketone and run it with our kinetic base. I need to be careful about equivalences here. If I add one equivalence of my aldehyde kinetic base with my ketone, that means that I'm going to turn every single molecule of ketone into an enolate. So I want to use enough that half of it turns into a ketone. So I'm going to add aldehyde at half an equivalence, 0.5 EQ. You could demonstrate this by saying 2 equivalents of ketone to 1 equivalence of aldehyde. That would get the job done. And I can see how that is kind of what it looks like is being said here. 2 of this to half of this. But really, I'm just putting this 2x to say that this happens with 2 equivalences of itself. Aldehyde is not a catalyst, though. Sodium hydroxide forms water that can be deprotonated in the end. Aldehyde cannot. So in this reaction, I'm going to need to follow this up with an aqueous workup. And here's that product that I get. The more substituted alpha is the one that attacks here. Excuse me, the less substituted alpha is the one that attacks here. Structural isomers, that's what we get. Regio control between using my kinetic base and my thermodynamic base. Okay, tomorrow we're going to look at the aldol condensation reaction. And then we're going to look at the Claisen condensation reactions. After we get through those, and we'll do a lot of practice problems with them, we've just got 2 reactions left, which is Michael addition and Robinson annulation. We're in the home stretch here. We're almost through. So keep your heads up and start reviewing. Now is the time to start reviewing. A week and a half before the final. All right? Have a good day. I'll see you guys tomorrow.